hear me okay? I'm in the middle of a grocery store. It's kind of having a weird one here. Good, green light, yes. Yes, yeah, good to go. We're good to go, or no, Shea, we're not good to go.
Shea, it's kind of loud over on your end. I'm not sure why.
It is, it is. I'm gonna record it, it is, and then I had one for you.
Okay.
I had a comment back for you.
And I had a, I was in, my father and I got my, and so.
I know, it's really loud. I have to watch that today.
When you guys kind of forgot to it. We were focused on up. You got, so we were.
So you had a couple questions.
Yep. We got it. Next, we got it.
Using formulas together. So today we're going to work with the chart a little bit and you'll get to see how things move or don't move and how they're related.
Okay.
So that should be better as far as like the verbal problems. So if you could say like, hey, my spatial pulse length changed, it increased, what else changes? You can look at that chart and see what else changes.
Okay.
So we'll utilize the chart a little bit today.
Okay.
And then what else do I have?
And I was like shocked.
Oh, Becky,
And we're like,
I had yours too.
And we both started having heart attacks. Yeah. That makes sense.
So the on time for PRP being 13 microseconds. So that's how long it takes to image. So in and out for 1 centimeter. So if it's 10 centimeters, it can be 130 microseconds. But that's the in and out time, and it's a constant. It's
a constant. Okay.
It's a constant.
Thank you.
Yep. And then you how do pulses relate to sound waves? So our pulse, that's the sound we're like chirping, right? So chirp, chirp, chirp. So that's the sound that's going out is our pulse.
Okay.
So they're the same thing.
Okay.
And then don't understand how the machine produces pulses to create scans. We'll get into what we call phasing eventually. We'll talk a little bit about it today, but there's an electrical impulse that hits these magic crystals in the transducer, and the crystals go from electrical to acoustic power. So the electrical hits them, and then they emit an acoustic power that goes into our patient's bodies. The acoustic power comes back in, the amplitude comes back in, and then it's then converted into an electrical impulse. And the amplitude of the electrical impulse, high is going to be very echogenic, mid-range is going to be gray, no returning echo is going to be black.
Okay. Thank
I
you.
need you to go away. Okay, and then you asked too, I know, he's here, I know, I'm trying to do this. So you ask about duty factor. So you can either say we're scanning at 10 centimeters. You can have a really long pulse, and so we have an increased duty factor. Or you can have very shallow scanning with that same pulse, and that will result in a high duty factor as well. So duty factor is calculated with your pulse duration as well as your pulse repetition period. Does that make sense? So you can have a long pulse, or you can have shallow depth with that same amount of pulse, and that's going to be an increase in duty factor percentage wise.
Okay.
Okay, so that was all Becky's questions. Okay,
Thank you.
who else do I have? Done. Who else is on my list? So one of the things we're going to talk about again today is going to be intensities and then duty factor. So we'll get into this a little bit right now. Anybody else have any specific questions before we get physics started? So your 105, go ahead.
It's not related to physics, but related to class tomorrow. So pathology is usually over Zoom. Are we doing that tomorrow as well?
Yes, yes.
Okay, so technically, unless we're going in for open lab, since Tony doesn't have class.
Correct, because you have your midterm this week. Correct, correct.
Okay.
And then your 105 midterm, it's posted in Canvas. I haven't published it for you guys. If you could return it by end of day today, so say 6 p.m. today for your 105 midterm, and I'll get those graded as soon as I can and get them back to you. And then I will be back super duper late Tuesday night. I think I arrive at like midnight at SeaTac, and I still have like a 2-hour drive. So I was wondering, Wednesday lab people, do you guys want to start a smidge later than 10 a.m.?
What time are you thinking?
Like maybe noon?
Sure.
Noon?
Yeah.
Anybody have a problem with that? Okay. Okay, so let's do some of this review real quick. I'm sorry, I'm like moving into your.
You're fine.
Sorry. Okay, so let's go over, we're gonna go over intensities and we're gonna go over duty factor. So let me get my whiteboard out.
How was that? Yeah, you're pleasantly surprised.
Okay, so when we've been discussing, let me hide you guys real quick. When we've been discussing intensities,
Maybe you could do it with the free champagne. I know, right?
there's two ways that we can discuss intensities. There's spatial intensity and then there's temporal intensity. And so spatial is going to be the one, this is not correct. What is even happening? So spatial intensity is our beam in space, and it's comprised of all these little teeny tiny temporal intensities, right? So we have all these little wavelets in here.
Is there a receipt for us to- No.
So spatial is a cumulative of this. And when we look at our spatial intensity,
Oh my God.
the portion that's the most intense is going to be proximal and down the center of our beam, right? Remember this guy?
Yeah, I gotta get no.
So this is our spatial peak.
Yeah, really only need to know.
And then we can take an average of all these intensities, so spatial peak as well as the intensities outside of our spatial peak, and this becomes our spatial average. And there's that beam uniformity coefficient. You guys remember this?
All right, we're gonna go get milk.
And that's our spatial peak over our spatial average to determine whether our spatial peak is significantly higher in intensity or lower in intensity than the spatial average. So we can describe this as spatial. So that's where our things are in space. And then let's go for temporal. How do I crew this? This is not what I had in mind, but okay, let's do it. You guys see my bullshit? Yeah, Shea, you can see your
Yes.
bullshit. Okay,
Yes.
good to know. Okay, okay.
Yes.
So. Okay, so let's look at one of these temporals. So that's one of these little teeny tiny lines that is our regular. So we have, here's our pulse here.
What are you doing now?
So we have two ways to describe it. Spatial, pardon me? Pardon me, girls, boys, women, ladies?
Hey, Kayla, I think you're on, you're not muted.
Oh.
Okay.
Hold on.
Actually, let me
Sorry.
get a little bit better angle here. It's okay. And by the way, I would like to speak with you afterwards because I have some homework to go over with you by yourself. Okay, so here's our pulse. So we have our on time here. We have our off time here. Okay, so we have different ways to measure. Now, this is one of our little teeny tiny, so our transducer is comprised of a bunch of little crystals. They're going to be electrically stimulated, and they have what's called the piezoelectric effect, and we'll learn about that later. But it goes from electrical to acoustic. So then what's reflected back from the body is acoustic, and it gets transferred back to electrical. So right now, we're just looking at our pulse. So the electrical pulse that's stimulating the crystals, and it's going to produce a sound wave. So we have over time, because it's a little chirp, it's like a bat. So it's going to chirp, and then that's going to reflect back, and the bat listens to it and knows the distance between the fruit tree or the vampire face or whatever. So it's going to know exactly how much timing delay is involved in that. So we have that. So this is one chirp. Our transducers are putting out about 300 chirps at a time. So the first way we measure this is going to be our temporal peak. Let me get a different color. So our temporal peak. So this is the peak of our first cycle. So that's the highest peak that we're going to have. So there's temporal peak. And then we have what's called IMAX. And IMAX is something that we totally ignore, but it's the intensity of the first half cycle. So it's this guy. So IMAX. And we kind of ignore him. And then we have our pulse average. So that's just the on time. So it's the average intensity just for the on time. So pulse average.
Have you heard anything?
And then we then calculate the on time with the off time. And that becomes our temporal average. So temporal average. We good to go so far?
Yes.
Okay. So let me erase all this shit. Erase, erase, erase. I want to erase all of it. So ranking these in order, your spatials are always going to be a higher intensity than your temporals. So ranking these in order, so we're going to have our spatial peak, spatial average, temporal peak, Imax, which we ignore, no one cares about him, pulse average, and then temporal average. And the reason we care about intensities isn't so much that we want to rank these in any particular order. Your book has a way that we can combine them in certain ways, but we really care about the spatial peak and the temporal average, because that is the highest intensity and the lowest intensity. And we looked at those rarefactions and compressions, and the biggest particle difference, we'll get into this again later, peak negative pressure. So the more refractions that we have, and then we have a compression, that's going to cause a lot of energy transfer, and that can increase the temperatures of the tissues. It can also create what we call cavitation. Like, remember when you guys are poor and you're eating ramen and you're boiling water and little bubbles start to grow? And so that can happen in the tissues as well. Remember we talked about absorption last week with attenuation styles? So that's what we're risk for bioeffects for. Any questions on our review from last week so far? You guys good to go? Okay, so the next thing I want to talk about that you guys had questions on was duty factor. And this has to do with the chart. So let's erase all of this. Okay. So duty factor. So duty factor is a measure of the power being done per time. And so if we look at our pulse, so let's draw a pulse in here. Ooh, purple. So say we're scanning at 10 centimeters. Pretend that says centimeters and not like a third grader wrote it. So you can have like a short pulse, or we can have a very long pulse. So the percentage of work being done by the green graph is going to be a higher duty factor. So pulse length comes into play, and then our PRP also comes into play. So I can have the same pulse length and scan different depths. So 1, 2, 3, 1, 2. So this one would be nearly 100%, right? 100% duty factor. And this would be maybe like 60. We're making this up. We're not doing the math on it. So we can have different duty factors depending on our overall pulse length. So how many cycles that we have per pulse, or our imaging depth.
But does not matter.
Does that make sense?
No, sorry, to me it doesn't. Sorry.
Okay. So let's backtrack a little bit. So we can have variable pulse lengths, right? So if I'm scanning at a depth of 10 centimeters and I have a very long pulse length, how come I can't see you guys? I have a very long pulse
30,
length,
40 minutes.
then I'm going to have a higher percentage of work being done compared to a short pulse length
Got,
scanning at the same depth.
2:30.
So
Okay.
I'm working an 8-hour day, and whether I'm doing work for 5 of those hours or 2 of those hours. So my pulse length could be 2 of those hours, not doing much work, low duty factor, or I can have an increased pulse duration. So an increased work day, and I'm doing 5 hours out of my 8-hour day. So a higher percentage of work being done. Does that make
Okay.
sense so far on the pulse
Yes.
length? So then we can also talk about that as far as our PRP, our pulse repetition period. And so we can have a pulse repetition period, we're scanning at 10 centimeters, or we're scanning at
So do I.
30 centimeters. And the pulse can be the same. So I'm still doing 2 hours of work. It's a matter of whether my work day is 5 hours or my work day is 10 hours.
Which says,
So if I'm doing 2 hours of work over 5 hours, high duty factor. If I'm doing 2 hours of work over 10 hours, very low duty factor. So our pulse repetition period is like how long our work shift is. And then our pulse is how much we're actually working.
Was there anything?
Okay,
Does that help?
yes.
Okay. Any other questions on any of that before we get into today's lecture?
What about those?
Shea,
Yes.
can you explain to me why length of pulse is related to the duty factor?
So, okay, so think about your length of pulse is the amount of hours. Okay, so you come on campus, you're on campus for 6 hours and you're doing homework and you're scanning, but you only did 2 hours. That's your pulse. You only did 2 hours worth of homework and scanning over that 6-hour day. Next day you come in, another 6 hours, and you are doing homework and scanning for all 6 hours. So your duty factor, how much work is being done, is going to be longer with a long pulse within the same amount of time. So if I'm scanning at 10 centimeters, that pulse length is going to change. So if I'm working 2 hours of my 8-hour day versus 8 hours of my 8-hour day, that's going to change the percentage of work being done. Does that make sense?
You're in the.
Yep, thank you.
You got it. Any other questions before we start today's lecture?
Can I just clarify what you said? So
Sure.
when you're talking about the pulse, you're referencing like, or you're comparing that to like the work that you're actually doing
Correct.
each day.
On time over off time, or you know what I mean? Like on time, how much work are we doing versus how long is this whole thing happening?
And then you said the pulse length is like your work day.
That's a measure. Well, yeah, but it's a measure. So think about your pulse duration is the amount of time that things are happening. Your pulse length is actually how lengthy that is in space. How long does that pulse take up in space? Your spatial pulse length. So does it take up 1 millimeter, 10 millimeters? And remember that chart. So if we look at that chart, let's draw the chart right now.
Did I put double-sided tape on the bottom and I stuck it up
Whiteboard.
in the doorway and it was just there.
Okay.
I should have kept it. Stayed there for 5 years.
Let me hide you guys real quick. Okay, so let's look at our chart. So if we look at our chart, boop, boop. You guys remember how to draw this? So who's this guy? So we have time up here, distance down here, yeah. So this
That's
would be
the
our period.
pulse.
The period, right? So that's the time that it takes one wave to occur. And then this whole thing is our pulse duration. Now, when we look at distance, this is our wavelength, and this is our spatial pulse length, which we're going to talk more about today in lecture. So pulse duration is going to be a measurement of time. How long does it take for our pulse to fire? So if we have boop, 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 a high frequency, that's not going to take much time for that pulse to occur. Let me move my menu here. Hang on. Get out of here. Get out of here.
I feel bad. So Sierra.
Jeepers. I don't even know what happened. What is going on here?
But we have to send Ashley to the office.
Ah.
But that's okay. 'Cause
Ah.
Sierra. Other Sierra.
Okay, well, that's it. So then we have a low frequency. So remember long, low frequencies. Long, low. So this is a low frequency. So this is not going to take much time to occur. So his pulse length, the distance that it takes up in space, is going to be decreased compared to this guy. So if I ask you about what happens if we increase our frequency, this chart is going to rotate back this way and look more like this. So that means our period decreases, our pulse duration decreases, our wavelength decreases, and our spatial pulse length decreases, which is good for resolution. Remember, we like very small spatial pulse lengths, very low numeric values. But if I say we're going to, let me go back real quick. But if we're going to lower our frequency, so decrease frequency long and low. So we're going to extend this out. So that means our period gets extended, our pulse duration gets extended, our wavelength gets extended, and our spatial pulse length gets extended. We're lengthening out that chart. Does that make sense? Any questions on the chart? So basically, if we increase our frequency, we have more cycles per second, shorter wavelengths. So that whole chart is going to compress itself. So the period on top, the pulse duration on top, the wavelength on the bottom, the spatial pulse length on the bottom, axial resolution, which is applying to spatial pulse length, all of that's going to minimize. If we decrease our frequency, we're going to lengthen that chart out. So the period's going to get longer. The pulse duration is going to get longer. The wavelength's going to get longer. The spatial pulse length is going to get longer. So our axial resolution is going to have an increased numeric value, which is bad. Remember Justin Bieber? I'm at the concert with Justin Bieber, and I want him to be able to determine me and my friend as separate structures. And so the better he can resolve me, the better numeric value, the smaller numeric value that he can distinguish me as separate, he's going to know that my friend and I are two separate structures, and I'm not just a giant person. Making sense? Any questions before we start lecture? Also, your physics midterm is open, I believe, this morning through Sunday evening. So let me know if you have any questions. And we'll go from there. You ready to start lecture, everybody?
Shay, real quick, how similar is our physics midterm to the mock midterm?
Very similar.
Okay, yay.
Yeah, very similar. There's like two big problem questions at the end where you have to do, like, remember the one we did in class where we did multiple steps, like, hey, we have to find the frequency, and then we have to find the period, and then we have to find the pulse duration, and we have to find the, okay, so it's like that. It's like a multi-step. So there is a couple multi-step ones in there.
Okay.
But you have 80 minutes to complete it.
Okay.
And just to confirm, you did mention last week that it is open book.
You can, yeah, feel free to use open book, open note, but for your own sake, when you have the SPI, you're not going to be able to do that. So I would try to, you have 80 minutes for 40 questions, 30 questions, I think. So try to challenge yourselves a little bit and just try without and just see what you can do. And then if you have to, fine. Doesn't matter to me, but try to challenge yourselves a little bit.
I think I saw it on the online. The question is a 30 question, but for 30 minutes. Maybe you change it.
I'm sorry, could you repeat the last part of that, Flora?
It's online the quiz. I mean, physics the quiz is a 30 question with in a 30 minutes. It's not, you say the 80 minutes.
I just changed it this morning. It should be 80.
Oh, okay.
I just changed it this morning. Yeah. So we should be good to go. I just changed it this morning.
Okay. Thank you. Let me continue to the class. Thank you.
Yeah, you got it. Okay, you ready to start our lecture, everybody?
Yep.
All right. PowerPointing my face off here. So share screen, PowerPoints. Do. Okay, let me move this guy. Okay, so we talked a little bit about resolution types, and we talked, just barely touched on it. We talked about how down your beam, it's that the waist of the hourglass, and where it's narrowest is your best resolution. That's how Justin Bieber tells me and my friend apart. And then we're also going to talk more about axial resolution, which was down our pulse itself. So one's across the beam and one's up and down the beam. And we want small numeric values for these. So when I say improved, that means small numeric value. When I say increased, that means poor resolution. So the higher the numeric value for our resolutions, the more poor we are at distinguishing me and my friend as separate at the Justin Bieber concert.
Hey, Shay.
Okay. Yes.
Are we?
Oh,
Oh, sorry. I thought we were on lecture 4.
Oh, didn't we do lecture 4?
No.
Oh, we didn't. Well, shame on me. Wasn't that our Okay, hang on. Download. Where are you? Okay, hang on. I gotta get you guys away. Download. Yes, please download. Oh, well, lecture 4, that's super easy. Okay, we got this, everybody. So let me do a screen share again.
Hey Shay.
Yes.
So will lecture 5 be on the midterm since you thought we were on lecture 5?
Let me double check, but I don't think so. Didn't we? Okay, you're right. Okay, attenuation. So tell me about the types of attenuation. How do we lose our beam volume?
Absorption.
Absorption, so that's loss through heat.
Reflection.
Reflection, we had a bunch of different subtypes to reflection. What were they?
Scattering, diffuse. And
Yep,
one other one.
specular, and that Rayleigh scattering, right? And so we can determine percent reflected at 90-degree incident, right? So what's our percent reflected equation?
Z2 minus Z1 over Z2 plus Z1, whole thing squared times 100.
You got it, you got it. And how do we determine our percent transmitted?
Subtract that from 100.
You got it. Okay, refraction. What is my favorite type of attenuation?
Refraction.
Refraction. So we have to be at oblique incidence for that. And then we use propagation velocities. And so the higher the propagation velocity gets the larger angle, whether it's incident angle or transmit angle, whoever has the higher propagation velocity, remember the alligators, gets the higher angle. Okay, so which of the following will result in a transmit angle that is larger than an incident angle? It's like we just talked about this. So we want a larger incident angle. So which tissue is going to have the higher propagation velocity?
The second one.
Yep, I don't know who that was, but yes, you are correct. So the propagation velocity of medium 2 is higher than the propagation velocity of medium 1. So our transmit angle is going to be higher than our incident angle. Good to go? Okay, next up. Which type of intensity is closely related to bioeffects?
Spatial peak temporal average.
Yep, so that's our highest intensity compared to our lowest intensity, that rarefaction and compression where our particles are moving. So SPTA. Okay, an increase in operating frequency will cause what changes? So this is our chart a little bit. So we increase our frequency. So does that mean our chart gets squished or it gets lengthened out?
Shrink.
It gets squished. So if we're squishing that chart, so we're going to see a decrease in period, a decrease in pulse duration, a decrease in wavelength, a decrease in duty factor, a decrease in spatial pulse length, and a decrease in axial resolution. So which one of these applies?
Decrease in spatial pulse length.
Correct. And why wouldn't propagation velocity be included in this?
Because it's not dependent.
You got it. It's a property of the medium. You got it. So we have no change over that. It's just whatever we're scanning. Okay. A decrease in PRP will cause follow the following except. So we're taking the very top of that chart and we're shortening up the imaging depth. What are we thinking?
PRF.
Well, so PRF and PRP are reciprocal. So if I decrease one, I'm going to increase the other. But let's think about what we're doing. So that PRP is dependent upon our depth button, right? So if I decrease my PRP, what am I doing? I'm adjusting that depth button. Right? Now think about our pulse. Did we change our pulse? So we changed our field of view. We changed our PRF because those are related, they're reciprocals. We did not change our pulse at all. So there's no change to our operating frequency. And so all of these changes will happen except a change in frequency. Does that make sense?
Can you say again?
Can you say it again?
Okay. So this is one of those all of the following except. So we decrease our PRP, we go to our little depth button and we're decreasing our depth. So we're going from 10 centimeters to 5 centimeters. So that means my PRF, I can go faster. I can put out more frames per second. So my PRF is actually increased. So that's correct. Duty factor. So I took my on time and my off time and I reduced my off time. So instead of working half the time, 2 hours out of my 4-hour day, now I'm working 2 hours out of my 3-hour day. So that was an increase in duty factor.
I feel that.
Decrease in field of view. So I'm taking that PRP and I'm going from 10 centimeters to 5 centimeters. So the only thing that didn't change was my pulse itself. So because I didn't change my pulse itself, there's no change in my frequency. So all of the following except, so no change in frequency for this. Does that make sense? Yes, Shay, this makes perfect sense. Yeah? Good to go? Okay, now we're taking that same portion of the chart and we're lengthening that out. An increase in wavelength. So what happens when we increase that wavelength? So we've taken that chart, our period gets longer, our pulse duration gets longer, our wavelength gets longer, our spatial pulse length gets longer. So that means our duty factor is an increase in percentage. So what are we thinking?
Increase in pulse duration.
You got it. Perfect. You got it, because we're lengthening that chart out. Okay, next up. Which of the following will result in an increase in axial resolution? Now remember, an increase is bad. Increase in numeric value.
You got your TG here.
So when we change that chart, when we lengthen that chart out, that's going to increase our spatial pulse length, which is going to increase our axial resolution. So what is it that we changed to lengthen that chart out?
Increase period.
Increase in period, you got it, because we remember our wavelength and we have distance on the bottom and time on top. So if I lengthen out one of those, the other one's changed too. So an increase in axial resolution means an increase in spatial pulse length, means an increase in wavelength, means an increase in period, increase in pulse duration. All of those things are going to lengthen out at the same time. Okay. You guys want to take a quick break so I can use the restroom? Yes?
Sure.
Okay, give me like a few minutes. It's 1:30 now, or you guys are at 10:30. I'm 1:30. I'm on East Coast. Let's be back here at like 1:40. And then you guys can go cry. You guys can go cry for 10 minutes.
Okay.
And then we'll start working on other stuff. Okay, give me a second and I'll be back in a bit.
Oh, I like
Okay, from current slide. Oop, 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 oop. Okay, so range equation, axial resolution, transducers, and the beam. So range equation. So this is kind of what we talked about earlier with PRP. So our machine is using a predictive value to determine the depth that it needs to put a reflector at. So if my beam goes in for 10 centimeters, so 130 microseconds, and my machine receives that at 130 microseconds, it's going to put that particular reflector at 10 centimeters of depth. And so range equation is also called the round trip or the go and return time. And so of course, it's going to be longer if we're imaging deeper. So if I'm 1 centimeter, that range equation is going to be 13 microseconds and then back. But if it's 10 centimeters, it's going to be 130 microseconds and then back. And so it's just our machine predicting, hey, this pulse came back at this particular time. So I need to put it at this particular depth on our image itself. So we talked about this with PRP. So what about reflections that return at unusual times? So say my machine receives one at 13.2 microseconds. It can either place it just slightly below a centimeter, but if it's not expecting that pulse to be coming back at 13.2 microseconds, it's going to disregard it as noise. It's basically saying this is static. It bounced around the body or it had like an erroneous thing and we're not going to display it. It's actually noise versus being our signal. And we'll talk later on about signal versus noise. So signal is what we're dealing with as far as like the actual returning amplitudes that are correct. And the noise is kind of a static. So you're listening to Justin Bieber on your car stereo and you can hear all of his amazing music, but then you might get some static. So if we had a really good car stereo, we could distinguish signal versus noise, and our car stereo wouldn't display or wouldn't you wouldn't have that being projected. So signal versus noise.
So she's a girl to start with.
So moving forward, we've talked a little bit about axial resolution as it applies to our spatial pulse length down the beam. We've talked about lateral resolution, that's that hourglass portion at the very center of our beam. And then there's also what we call a slice thickness. So slice thickness, if you think about our hourglass, there's a side to side on our hourglass. There's also a front to back on our hourglass. And there's ways that we can manipulate the thickness of both of those because we want a very low numeric value. Now, looking way down ahead, we also have temporal resolution. So how fast my machine can make our images. Remember how we wanted to have like 1 or 2 focal zones for deep scanning versus having a whole bunch? So if I have a whole bunch, my machine has to process all of those separately. Or when your color box is too large, it has to image those separately and then make the image out of them. So our temporal resolution is basically like a flip book. How fast can we make these images? And then we have one that we'll talk about again next quarter called contrast resolution. That's basically the numeric values of grayscale. So how good am I at distinguishing 2 structures as separate based on their grayscale? So let's review again. Axial. How good am I at distinguishing 2 structures as separate down my beam? Lateral, across my beam. Elevational, front to back of my beam. Temporal, based on time. And then contrast based on grayscale. So how are we at distinguishing 2 structures as separate based on all these factors? So there's a lot of names for our axial resolution. And we'll talk about this at the end. I have a little slide for you guys, but it's called LOT-A-LARD. And this is the LARD. So axial resolution has multiple names: longitudinal, range, radial, and depth. So LOT-A-LARD. This is the LARD. So this comes back to our spatial pulse length. So the longer my spatial pulse length, I'm going to see 2 structures as separate because my chirp is going out and it's coming back, but it's not chirping off of those things individually. And so I'm going to have a spatial pulse length and it's going to cover both of those structures and it's going to look like one large structure. Smaller numeric values are always better. So when I say improve or better lateral axial resolution, that means a small numeric value. When I say increased axial resolution, that means a larger numeric value. So that's Justin Bieber not being able to distinguish my friend and I as separate. So larger numeric value for axial resolution. This is one of the reasons if I take a high frequency and a low frequency and compare them. So I have 3 cycles in the pulse. My high frequency is going to be very, very squished together and very, very small. Whereas my lower frequency is going to be much more lengthened out. So we can penetrate better. Remember those rarefactions and compressions. I can get better penetration through the lower frequencies, but I don't have the ability to resolve things very well as 2 separate structures in the body. Making sense so far? Good to go? Okay. So we have 2 axial resolution equations that are different than the ones you've learned before. The easiest one to use, and it's in bold, is spatial pulse length divided by 2. You could also use your wavelength times your numbers of cycle. Notice your wavelength times your numbers of cycles is the same as your spatial pulse length. Or you can take 0.77 times the cycles in your pulse and then divide it by your frequency. And that one's a little bit more cumbersome to use. So I would stick with your spatial resolution divided by 2. Okay, good to go so far on axial resolution? So we spoke on this a little bit earlier. So a transducer, so whether it's in your car stereo or whether it's our probe, basically we're transmitting one type of energy into another. So we are putting an electrical impulse into our magic crystals, and then they're emitting an acoustic impulse that goes into the body. That acoustic impulse is reflected back, and then it's transferred into an electrical impulse again. So the higher the volume that's going out into the body and being reflected back, the higher the amplitude, so the higher the brightness of our electrical impulse being returned to our transducer. So that's how our machine knows something is echogenic or it's anechoic. So I put sound out and it doesn't have any kind of reflection, comes back, 0 amplitude. So that's our anechoic stuff. So there's nothing reflecting back. Conversely, we look at that gallstone or the specular reflectors such as the diaphragm. So my beam goes in. This is why I like my aorta is nice and flat, right? Nice and perpendicular. So our beam goes in, it reflects a lot of its amplitude back. So it's very, very bright. So low amplitude, going to be anechoic, low level gray. High amplitude returning is going to be brighter, light colored gray. And the way that we talk about this is the piezoelectric, which I think I pronounced this wrong. I think it's actually piezoelectric or ferroelectric effect. So that's what our machine is doing. So when we look at transducers, when we look at the parts of a transducer, we have the case, right? You guys have all touched this thing. This is actually what is it housing all of our material in there. Then there's an electrical shield and an acoustic insulator. So we have to insulate against electrical impulses. So I'm up in the portable ICU unit and I've got, you know, the ventilators on. There's these things that compress legs that are on. I have all these electrical things going on. So I need to be able to insulate my transducer from receiving outside electrical impulses. And then we also have an acoustic one. So not that you would like yell into your transducer and have it like do anything, but the idea that if there's an acoustic impulse that's coming in and going to affect those crystals, that will result in an erroneous reading. So we want to make sure that we're insulated from both of those things. And then we have the actual PZT or the crystal. So this is where the energy exchange occurs. So lead, zirconate, titanate. That's the PZT. Lead, zirconate, titanate. And so electrical impulse goes into this, piezoelectric effect happens. So electrical impulse kind of shakes those crystals up and they emit an acoustic energy. That acoustic energy goes into the body, reflected back at a specific amplitude, and then that's turned back into an electrical impulse. And then we look at it and see like, hey, is it bright or is it not bright? And the thickness of our crystal is 1/2 of our wavelength based on frequency. This is a little bit erroneous way to think about this because now we have multi-frequency probes. So you guys all touch that megahertz button that Mike loves so much in class. So you can actually go from a 6 megahertz to a 4 megahertz or down to a 2. And so prior to this, we had just one frequency that would come out of these transducers. And so our crystal thickness was 1/2 of the wavelength of whatever our frequency was. And there's a diagram in your book about it. Next up, we have a wire, right? We need wires to emit electrical impulses and then receive those. So making sense? And then there's 2 layers. There's a matching layer and a backing layer. And these are very, very important. And we'll talk a lot about these in the future. So make sure you remember these. The matching layer. Remember how we talked to you guys last week about the occludence and impedance and how willing or unwilling a tissue or particular area is to take our beam? So if we just put our probe on our patient's tissues without any gel, we don't get any kind of transmission. We get all reflection. And so we have a matching layer, and that matching layer is midway between the patient's skin and our transducer crystals. So it decreases the acoustic mismatch. So it's like a little stair step. So it's stair stepping down between our transducer and the patient's skin, and it's stair stepping so that we can have transmission. Additionally, our gel does this as well. So it has an acoustic impedance that's between the matching layer and our patient's skin. So we're making smaller and smaller steps to bring that transducer kind of amplitude within our patients. And then we have what's called a backing or dampening material. And this is interesting. So we've talked, let me share screen real quick. We've talked pretty generically. Let me get my whiteboard. We've talked pretty generically about what our pulses look like. But what they truly look like. Yes, whiteboard, yes. Okay, let's clear all this. Clear. So when we look at a pulse, right now, get over here, buddy. Draw, yes, draw. When we've talked about pulses, we've talked about them being pretty even, like this. But normally, it's like a ringing of a bell. So they have high amplitude, kind of going into ringing. And so this is what our pulses actually look like. And so what our backing material does is it insulates against that additional ringing. So instead of having a pulse that looks like this with these additional little spots on them, because again, spatial pulse length, right? We want to be able to distinguish two structures as separate. What it will do is it will insulate that. And it's kind of like putting a gong on our bell. So now we can distinguish two structures as separate because it's reducing the ringing of the spatial pulse length. So it's improving our axial resolution. Does that make sense?
Can you say that again?
Sure. Okay, so let me go back. So the backing layer, let me just clear all this. So the backing layer acts like, okay, so I've got a bell in one hand and it's like ding, ding, ding. And then I have a bell in my other hand, but I have my friend is holding my bell. So it only goes clonk, 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 right? It doesn't ring. And so we've talked about pulses pretty generically, but what they are is they're a high amplitude and it's like a ringing of a bell. So they'll have continuous kind of like the ringing portion. And so what our backing layer does is it insulates against that. So this is your friend's hand holding your bell. So instead of having a nice resonant kind of elongated ring, it's going to just give it a little clonk, and that's how it ends up. So where we had spatial pulse length here was very long, right? Increase in spatial pulse length. Here, when it's insulated, we have a smaller spatial pulse length, so that improves our axial resolution. Equals better. So that's the whole purpose of that backing layer, is to improve our axial resolution by reducing the ringing of our crystals, the ringing of our little bells. Does that help? And keep in mind to have, go ahead.
So the backing dampening material improves their axial resolution
by giving it a smaller numeric value. So improved is small numeric value. I want Justin Bieber to see my friend and I as separate. So he needs a decreased numeric value of resolution. So improved is narrower, like smaller.
Okay.
And you'll forget that. Don't worry. You'll forget it.
Thank you.
Got it. Okay. Next up.
Then I was like, and it all led me to being here, you know?
Okay, so these are, oops, these are just parts of our transducer. So we talked about this matching layer. So we're basically encouraging more transmission and reflecting by using that matching layer. So we're trying to get more of our beam to go through the tissues. So through our transducer, through the gel, into the tissues. And so it's going to step down that acoustic impedance mismatch. And gel is also called a coupling agent. So you might see that in some of your literature as you guys are studying, coupling agent. Okay, backing, excuse me, or dampening. So this is going to decrease that spatial pulse length. So it's better axial resolution. And then sensitivity. So if my machine is very sensitive, it's going to display all of those little tiny amplitudes as signal versus noise. You want decreased sensitivity, like our high school boyfriends, right? You want decreased sensitivity, so you're not displaying, you're not overly displaying noise, but you're not under displaying your signal. And then let's talk about bandwidth. Bandwidth is a measure for us to discuss how many frequencies, what range of frequencies our machines can work in. And so if I have a high or a low bandwidth, okay, so this is how it goes. So your neighbor is stealing your Wi-Fi and they're watching pornography and it takes up a bunch of your bandwidth. And so when you're trying to watch YouTube videos, it's like herky-jerky starts and stops because they're taking up your bandwidth. So if you have a wider bandwidth, your neighbor can watch pornography and you can still watch YouTube videos. Not that any of you watch pornography. So here's how it goes. So my bandwidth is my range of frequencies. So here's my usable frequencies. Like for our machines, we use like say 2 to 5. And then we have a, oops, I lied. Let me go back. Boop, 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 boop. So we're using a 4 megahertz, and our machine can read a 2 to a 6. So our bandwidth would be 2 to 6, so 4 megahertz. So our bandwidth is 4 full megahertz worth. So I can work in a 4, I can work in a 3, I can work in a 5, and I can work in partials of those too, 3.5. 5.5. Now, why is this important? This is important because this allows us to run color Doppler at one particular frequency, spectral Doppler at an additional frequency, and then our 2D imaging at a third frequency. And we start getting into harmonics next quarter, and harmonics is actually double your initial frequency. So if I put a 5 megahertz in, it's actually going to become a 10 megahertz. So we need a really, really wide bandwidth for harmonics. But for this, we just need to worry about, like this quarter, we just need to worry about working in Dopplers. So spectral Doppler, color Doppler, power Doppler, and my 2D imaging. So we need to have a wide bandwidth so I can dedicate one frequency to color, one frequency to my 2D. And the way we discuss bandwidths is what we call the Q factor. And the Q factor is a unitless number that describes basically our range of working frequencies compared to what our initial frequency is. So if I have a Q factor that's very high, so 1-to-1, I'm only able to work at a 5 megahertz, and my machine only works with a 5 megahertz. So my Q factor equals 1. So we want a low numeric value for Q factor. That indicates that we can work in multiple frequencies. So like 0.1 would be great. So we want a decreased numeric value for Q factor. It's just a measure of our bandwidth compared to what our primary frequency, our operating frequency is. So the larger the range of the bandwidth, the lower the numeric value my Q factor is going to be, which is desirable. You will never have to calculate this shit. It's just something you need to know for the SPI. No radiologist has ever asked me about my Q factor, ever, on Earth. Making sense so far?
Yeah.
Yes. Okay, good to go? Okay. So let's go back to our PowerPoint.
Almost got elbowed. Oh my God.
Okay, from current slide. Okay, so wide bandwidth indicates a low Q factor. So the larger my bandwidth is, the more variable velocity, variable frequencies I can work in, which is going to be a low numeric value. So wide bandwidth, good. High numeric value for bandwidth, which is a low bandwidth Q factor numeric value. So sensitivity we talked about a little bit. So how well our machines distinguish signal from noise, bandwidth, the range of frequencies, and the Q factor is a descriptor used to evaluate our bandwidth. So decreased sensitivity. So basically we had that that dampening layer. So we knocked off a bunch of the additional ringing from our pulse. And so that decreases our numeric value of axial resolution, which is improvement. But if we have too sensitive, so high school boyfriend, then all the noise is going to get displayed. So we're going to have all of the static basically being displayed. But if we have too little sensitivity, so this is more like college boyfriends, too little sensitivity, in that case, what we would have a low amplitude signal, so like a very low level gray, wouldn't be displayed. Our machine's like, yeah, that's fucking garbage. They call that the reject. And we'll talk about this with receiver functions, but our machine is rejecting things. Just like Shea in high school at prom. I'm getting rejected. And so there's a certain level of rejection that we aim for. Too sensitive, we're going to not reject enough of the low level echoes. High sensitivity, like, okay, we're going to see a lot of noise. But if I'm too little sensitivity, I'm going to start eliminating some of those low level grays. And sometimes I need to see those. We talked about within the IVC or within the aorta, some of those low level grays, it can be subtle plaque or thrombus accumulations. So if a machine is too dismissive, too rejective of these, they won't get displayed, and we want to see those displayed, those subtle pathologies. Okay, wide bandwidth. So we talked about this already. So basically, I want to be able to work in a multiple frequency range so that I can work with color with one, with 2D with another, and with spectral with another, and maybe even some M mode, which we haven't talked about. But the number one reason, and we'll get into this next quarter, the number one reason we want a large bandwidth, low Q factor is when we're working with harmonics. Because what we do is we put out this inverted pulse, it goes out as a 5 megahertz and it comes back as a 10. So it needs a very, very wide bandwidth. So here's our Q factor equals frequency over bandwidth. I don't know what happened to my slide, but we take our primary frequency, which is maybe 5, and our bandwidth is like 2 to 6. And so a lower numeric value indicates a high numeric value for my bandwidth. Okay, sound making crystals. We talked about this. So basically we have all these crystals on our transducer, and what happens is they'll line them up, and it's lead zirconate titanate, so PZT. So they'll line these up and then they'll put them in a heater, and then they put a magnet on them so that all of the electrons go in the same direction. So that when we have the electrical impulse going in, everybody's sending the acoustic the same direction. When we have the acoustic coming in, all the electrical is going the same direction. And so they call that polarization. And then don't be a Shea and loan your transducer to the ER, who puts it under a steam autoclave and fucks it up, and then the polarization is lost. So when it gets super hot, those electrons will then reconfigure themselves, and that's called the Curie point. And so when the Curie point happens, then we lose polarization, and our transducers don't work with the shit. Then Shea gets a meeting with the supervisor, and it's a big ordeal. So we can steam autoclave other things, but not your transducers. And instead we do chemical autoclave, or we just do a what we call a Sidex rinse. So okay, so this, I actually have a really good way to think about this. So probe frequencies. So keep in mind too, these are a little bit, this is like a little bit limited way to talk about this because we have those multi-frequency transducers now. But just in general, there's 2 ways when they were starting out the creation of probe frequencies that we could talk about this. So there was thick probes would have low frequencies, thin probes would have high frequencies, or we would evaluate the propagation velocity. And so they started using quartz initially to make ultrasounds, and now we use that PZT stuff. So there was like a variety of composite materials that they used in there that were different propagation velocities. But this is what I think of. Okay, you go to Walmart, you see some methed out person. They're thin and they're fast and they're high frequency. So thin, fast, high frequency. Thin transducer thickness, fast propagation velocity, and they're high on methamphetamines. So it's a high frequency. So that's the way I think about it. So they're thin because they're druggies. They're fast because they're speedy meth heads. And then so they're high as shit because they're using drugs. So that's how I think about that for frequencies. But now these days we're a little bit different than this, and we'll talk about this as we get into the development of probes and things. But this was just a very basic, when they were trying to figure out how to do ultrasounds, trying to figure out exactly how ultrasounds worked. And so this was it. They would use a different thickness, or they'd use a composite of a different propagation velocity. So here we go. Here is your equation. It's not necessarily that you're going to have to calculate anything, but they're going to say you have a composite material of X thickness or Y thickness. Which one's going to have the higher frequency? Or you have a propagation velocity of X or Y, which one's going to have the higher frequency. So you don't really have to calculate this. You just have to know thin and fast equals high. That's it. Good to go.
Can you click back to that very last slide really
Sure,
quick?
sure.
Thank you.
Maybe. Oh, let's say maybe, because I'm not doing a very good job right now. Okay. Boop, boop. Boop, boop. Oh. Oh, wrong one. I effed it up. Hang on, hang on. Shea's effing it up. Shea's effing it up. What's even going on here? Okay, okay, got it. Okay, okay. Yes, where's my mouse? My mouse has disappeared. My mouse is gone. Who stole my, which one of you stole my mouse? Okay, okay, where's my mouse? My mouse is gone. Jeepers. Okay, now let's go back. Okay, this one, the equation.
Yes.
Okay, so your frequency in your frequency in megahertz is the propagation velocity of whatever crystal style you're using. In our world now, we use the PZT. the lead zirconate titanate, and then it's 2 times your crystal thickness in millimeters. And again, you're not gonna have to calculate this. They're just gonna say you have a thickness of A or a thickness of B, which one's gonna have the higher frequency? Or you have a propagation velocity of A and a propagation velocity of B, which crystal is gonna have the higher or lower frequency?
So this kind of is like what you were explaining about it was like your tip of the day where it was like A equals B over C.
Absolutely,
So
you
in this
got it.
case,
Yep.
the frequency is directly related to C.
Correct. So the higher the propagation velocity, the higher your frequency.
And then
Now, if we look at the bottom, the lower your thickness, the smaller numeric value of your thickness, the higher your frequency. They work in opposition. So
So-
directly related to the top of the equation, indirectly related to the bottom of the equation.
Okay.
Good to go?
Yes.
Anybody else have any questions for me?
Can I ask a patho question?
Sure,
Just about the homework. So
sure,
would it be okay if we like took a picture of our homework?
absolutely. Yeah,
Okay.
absolutely. Yes, please. Yes,
Okay. Thank you.
yeah. Any other questions?
So is the pathology is going to be due tomorrow still? Or
I won't be home tomorrow, so on your lab day. And then Wednesday
Okay.
lab, we're gonna start at noon. Cause I don't get until like midnight, it's still like a 2-hour drive home. So Wednesday lab will start at noon. You have your AAA scan exam. Thursday lab will start regular time. AAA exam, 10 a.m. You have on 105, in fact, let me do that right now. On 105, I'm gonna publish your midterm. Please return by 6 p.m. today. Let me know if you have any questions. I'll be floating around. Files. But there is some drawings on it, so you will need to either print it out or take a, do it on a different sheet of paper and then send it to me, something like that.
You
I'm
want us
publishing it
to-
right now.
Do you want us to email it to you, or is there a submission on Canvas that we use?
There's no submission on Canvas. Email would be best. It's easier for me to sort it out if I can just go through my email and look at it.
Okay, so just make it into a PDF and email it to you.
Perfect. Yep, that would be great.
Okay.
And then if you need to do drawings, feel free to just do them on a separate piece of paper. Remember like the pancreas picture that I love so much? Yeah. So maybe study that guy a little bit. And then I'll see you guys online for patho. I'll get your patho PowerPoint rolling today at some point. And we'll go from there. How's that?
I gonna open 105 right now.
I just published it. So you should be able to open it now.